Welcome back, car and tech fans. In our last video, we took a look at how to actually look at the bits of data that are coming through from your CANBus using a tool like SavvyCan in order to pick out some things that we might be interested in displaying around the car, things like temperatures and pressures and speeds and all that kind of stuff. We looked at doing it live, sat in the car, and in this video we're going to take a look at how we would take an export of all that information that we've captured from the car in order to find the things that are a little bit trickier to find. Things like speeds and RPMs and temperatures and things that require you to be moving in your car or let it run for a long time and that change slowly over time. We're going to look at what, in my opinion, is the best way of graphing all this out because it is super easy when you know what you're doing with it. And for this video, we're going to be using SavvyCan, which we have been using for the whole rest of this series. Really good, free analytics tool for your CANBus. And in this load up that I've got in front of me here, we have basically a file that I captured on a 10-ish minute drive of my 350Z, and it's got all of the information from every single ID in here. If you would like to play with this data dump that I've created, there's a link in the description to a Google Drive where you can download the GVret file, and you can just literally come into SavvyCan, load log file, and then load up this GVret file, and you can look at the exact data that I'm looking at if you wanted to play with the export from a 350Z, or you just don't have an export from your own car to look through in order to, start digging around in data for the first time. If you remember in our previous episode, we were using FlowView, and this was really useful when we were sitting live in the car and seeing which bits of data were changing, and using that we were able to identify things like the fact that 60D here was running our lights because we could see things changing in there. And we had some candidates for other things like oil temperatures, oil pressures, water temperature, speed. We had some ideas of what we thought they were probably going to be based on how we saw this thing move. But it's a lot easier to find those things when you have a mass of information. And that's what we have here. We have, like I say, about 10 minutes of driving data. So there's a better way of showing this information in SavvyCan and a better way of confirming what things are by comparison. So if we close off FlowView, we're going to Tools and Frame Data Analysis. And here it is. So what we have here is the two things that you're probably going to be most interested in is the interval histogram at the bottom left, but the big one is the bottom right, this byte graph. And this is all of the information over the entire time of the dump. So this is a approximate 10-minute time. Now, in some IDs like this one, it just looks chaos because of the things going from extreme 0 up to the extreme 255. And if you remember from our previous video, 255 is the maximum value we can hold in a single byte. So that's things going up and down between their extremes. So how do we use this to start looking for things that we're interested in? Now, we had a couple of candidates. So, for example, we thought that maybe 551 had one of the temperatures in it. As we can see, it starts down at 50-ish and it climbs all the way up to here, which is 120-ish. So we can probably safely assume that 551 is a temperature getting up to temperature. But we had a couple of other candidates that looked very similar, which are 233, and you can see there that blue line that runs on 233 looks similar. It starts a little bit higher and ends a little bit higher, and 23D. And it has another one that runs in a very similar way. But we can see when we quickly switch between 233 and 23D that those two graphs are the same. There's not a slight variance between them. They're identical. So whatever that value is, it's exactly the same. Now, it doesn't quite line up with 551, but it looks, especially if you see this part here, like it's probably the same again, but with a different offset. And we can confirm that using a second really useful tool, which if we go to RE Tools and we go to a graphing window, we can start a graphing window. Now, this is where things are going to get, I think, really interesting. This is just a graph, nothing on it yet. If we right-click and go to Add New Graph, we'll get this. Now, I'm going to just show you what this means. So this is the 8 bytes here, and then the bits for each one of those bits. So as we said before, each byte, so 1 byte here, is made up of 8 bits, from the least significant over this side to the most significant over the left. So each ID is 8 bytes of 8 bits, or 64 bits total. Before I add anything onto this, I'm just going to bring up that analysis tool again, look at 551, and we're looking at byte 0. So this one here is this dark blue one. So byte 0 from 551. And then these two that we know are the same, 233 and 23D, we can take either. And this one, 233, is byte 0. And this one, I think, is byte 7. Yeah, so we'll take 23D byte 7. Let's go back onto our graphing window. Right click, add new graph, and like I say, we're going to call this one, we'll call this one 551, and we're going to use the ID 0551. We want to look at the information that's being put out by byte 0, so that's this top one here, and we're interested in all of the bits that are within that byte. So it's an 8-bit data length, and we're interested in it from the start. So these first 8 bits. So what this is doing is saying, unlike a flag type where we're just interested in seeing 1 bit and how that 1 bit potentially turns on and off, we're interested in the whole byte because it's setting up a range, a thing that goes up and down from a 0, 0 all the way up to a potential FF. Right now, I'm not going to worry too much about these endian signs, mass by scale strides. I will tell you what they all mean in a minute. So we're just going to add that graph, and there we can see this is what that looks like over the entire time of our recording. But how does it compare to the other one? So if we add another graph, and this one is an analysis for 23D. So we're doing on ID 023D. Then this again has a data length of 8 because we're interested in the entirety of the byte. And this time it's byte 7 that we're interested in. And again, let's not worry about any of the modifiers right now. So if we add that graph, you can see that they are exactly the same, but there is an offset difference between the two of them. So one of them is just the same as the other, but slightly higher, which is good in a way because it means we only need to worry about one of these things. They're all just reading the temperature in some way. So whichever one we pick to use for our aftermarket gauges or to display the information about the water temperature or oil temperature or whatever it is, doesn't really matter. So long as we get this offset correctly, it's all going to give us the same result anyway. So we can use any one of these 3 bytes of data to display what we're looking for. So that's a nice, easy example where something rises. And I can tell you now, this is water temperature. And we know that it's water temperature in the 350Z for 2 reasons. Oil temperature doesn't exist on the CANBus in the 350Z. And oil pressure doesn't exist in the CANBus for 350Z. So neither of the 2 bits of information that I want to capture and put on my gauges actually exist in this data, which is disappointing, but there are ways of capturing those bits of information. But over the next couple of weeks, we are going to look at how we capture raw analog voltages that come from the senders and the sensors, and how we then convert those into numbers that we can use on our display. So never fear, even though the information is not on the CANBus, doesn't mean we can't get it. I also know that this signal, 551, is offset by 40 degrees. So this is actually the reading in Celsius offset by 40, What that allows it to do is go down into negative numbers without using a signed integer. And a signed integer allows you to go from a negative max through to a positive max, whereas an unsigned integer, which most of these are, only allows positive values. So by having a negative offset means that it actually can show a negative temperature even if you're only using a positive number. So this one has been discovered. So I'm treading on the toes of many other people's work. In fact, I had a lot of help with this by fellow YouTuber MotorVateDIY Garage over in Canada. Definitely go check out his stuff. He's doing a load of this for the Infiniti G37, which is basically, internally at least, the exact same as the Nissan 370Z, which in turn is very close to my 350Z. So a lot of this work has been done by other people. And we know that that minus 40 is the offset that we have here. So we can look at these extra values. Let's not worry about little endian for now, because we're going to look at that in a second. But signed is exactly what I said. Is it a number that allows to go negative and positive? Most of the time it isn't. Mask is what we would use if we were only interested in certain elements of this. So if we didn't want to include this fifth bit here, we would turn the fifth one of these off, and then that would not show the information from this fifth bit. Bias is how much do we add or subtract to the final value in order to make it what we want. So in this case, we know that it should be minus 40. Scale is what we will be using in a moment to make things bigger or larger by a factor, whereas stride, if we look at all of these kind of individual moves here, you can see that they keep, having these little micro jumps, because obviously it can't create a completely smooth line. But stride would be saying how many of those to use. So if we set it to 5, it would use every fifth reading in the output. Generally, we're going to want a lot of information, so every one is great. So that's what these things do. And with a combination of them, you can get from the input value that the car is generating through to the output value, which you see. And like I say, all we care about with altering this one is the bias. So reducing it by 40 degrees. So if we add that, we'll see here the temperature has dropped. So it's come down 40. So it starts now around 15 degrees, which is kind of what the ambient temperature was when I got in the car. And it tops out at 75, 80. So yeah, it tops out at about 80 degrees, which is correct for coolant temperature. So this is my coolant temperature graph, and this is how I'm going to be using it. 551, the first byte, so byte 0, with a bias modifier of minus 40. So when we're using this in our Arduino, we can just take a quick look at this. I'm not going to get into this too much, but when I'm processing the coolant temperature, which is just being passed through, if I hit ID 551, I process the coolant temperature. All it's doing is taking that whole string of all those bytes, it's grabbing byte 0s minus 40, and that's this, what I call this Nissan modifier value. It's just a thing that's specific to my car, which means in this sensor data function, we're now holding the water temperature, and it's updating, several times a second, I think. And it's going to be dead easy to display on our gauges. What about something that is not just a simple 00 through to FF single scale value? What about something that has a modifier byte or a least and most significant byte? How do we find those, and how do we plot the two together? Again, it's actually pretty easy. So let's find a candidate first. So we'll go back into frame data analysis, and I'm just going to jump to a couple that I know to be candidates. So if we go to 6F1 down the bottom here, there are these which look suspiciously like speed graphs. And when I went driving, I basically drove predominantly in 30-mile-an-hour zones, then went up to a 40-mile-an-hour zone, had to stop, came back along the 40-mile-an-hour zone very briefly, and then back into 30s again. Now this CANBus data I know to be in kilometers an hour, so we just need to look for those things in a slightly higher amount. So 30 miles an hour, looking for about 48 kilometers an hour, and 40 miles an hour is about 64 kilometers an hour. If we look at this, this very much looks like what we would expect that to look like. So in kilometers an hour here, this is the 40 mile an hour zone, which is topping out kind of mid 60s. And then we've got the 30 mile an hour zone here, which is kind of upper 40s. So this looks like the right kind of data for speed. But when we zoom in, we can see there's lots that have the same. So if we just start to delete the ones that definitely aren't it, so the yellow line at the bottom, purple one, the grey one, it leaves us with these four, which are all basically the same. So if we take a look, that one, red there is that line, black is there, green is there, and 0 is there. So how would we have 4 inputs that are almost, but not exactly the same? And if you notice, they tend to separate when we're going through these curves, these change curves. And that's because these 4 are wheel speed. So we've got the individual 4 wheels, and these separations are when we're going around corners, because the outside wheel is obviously moving faster than the inside wheel. Now, it is probably a smooth enough graph that we have to use as our speed, but there are probably better candidates, because our car isn't going to read speed based on one wheel. It's too inaccurate. It's going to somewhere have an amalgamation of these values. When we start looking through these other candidates, 354 was the one that was been our big candidate so far, because look at that. That's a nice, smooth, really consistent kind of output of what we would expect speed to look like, but it's not very big. And we also have the byte that follows that line that we can see down here. So that line is byte 0. Byte 1 follows it in a similar way. So if we look where we stop here, this is where we have a short break. Both of those values stop, so they're probably related to one another. If we can just hide a bunch of these other ones, because it just shows that we don't need them. So we're interested in these 2. And the reason we've got 2 is we've got the first one as the most significant byte. And it's the one that shows like the big part of the number jump. If you remember from our previous video, we said we can put 2 bytes together and it gives us a value up to 65,000 in decimal. What this means is this first byte is changing the big half of the number, the 8 bits on the left-hand side, whereas the right-hand side, they're smaller numbers, but they go through the entire range. So it'll go from 00 all the way up to FF and then flick back down to 00. And when it flicks back down to 00, this one on the left-hand side, the most significant byte, jumps up a level. So you can actually see how these things flick up and down in relation to that other byte. So what we want to do is use these 2 bytes together to create an even smoother graph, because what will happen is this green one will actually fill in kind of like where in each one of these steps it really is. So instead of just being the top and the bottom, it'll be somewhere in the middle. So it will create a smoother version of this graph. So we're doing this with ID 354 bytes 0 and 1. So let's just go over to our graph window, create a new one. And like I said, it's in 0, 3, 3, 5, 4. And this one is going to be speed. And we're interested in byte 0 and byte 1. So we're interested in 16 bits. So that encapsulates both of them. You might remember in the previous video, again, we spoke about big and little endians. In this case, we're looking at a big endian, which means the big bit, the larger part of the number, is first, the smaller part of the number is second. It's in a natural order, like the order you would read it. If, in some cases, which we can potentially look at in a moment, they're flipped and the larger part of the number comes afterwards, like as a flag, then it would be a little endian, and we would need to tick that box, and then you would select it like that, which means it would read in both directions. We're not looking at it like that, though. We're looking at a big endian. So this byte is the most significant one, and this one is the least significant one. So let's just start by throwing that out onto this graph and see if it creates a smoother version of what we'd expect. There you go. Now you can see what has happened is that the least significant bit has smoothed this graph out. You know, it's still a little bit erratic, as you would expect things to be off a variety of sensors, but it is a smoother version. But the numbers are real crazy big. They go up to 52,000 at the top. We don't get anywhere near 52,000 or 64 up here. So what this is, it's 100 times too big for the kilometers an hour. So if we start by editing this and give it a scale of 0.01, that'll reduce every number by a factor of 100. So we're reducing 6,000 down to 60. So if we just modify it like that, there we go. As we can see, that is now down at a right kind of number. So 64 kilometers an hour is where I maxed out at. So this is roughly our kilometers per hour speedo. But I don't run in kilometers an hour, I run in miles per hour. So there needs to be a bit more conversion in order to convert it from kilometers an hour to miles an hour. If we take a peek at our Arduino file, this was the number I was using, 621371. So that's how you convert kilometers an hour to miles per hour. 1 mile an hour is 1 kilometer per hour times by 0.61371. And that's going to give a close enough value. So when we come back into this edit, instead of doing 0.01, we would swap that 1 for 0 and then that value that we've looked at, 0.62. So this will convert that 6,000-ish number down to around 40 miles per hour. We change to that, and we can see. So this is where my 40 miles an hour limit comes in. Now, what is interesting is I sat, according to my gauge, at bang on, roughly, you know, as much as I can hold one speed constantly, 40 miles an hour for those 30 seconds that I was on that bit of road. But it shows that the speed that it was reading was actually 38-ish. So it's actually showing a number out, which is a couple of miles an hour more than it's reading, which is a thing that a lot of manufacturers do. They give you that slight buffer to prevent any chance of the speedo gauge reading less than the speed you're actually doing. So it's never going to read 30 whilst you're actually doing 32. They give a little bit of buffer in there. So we could do this by adding a single mile per hour, but that wouldn't work because then when we were sat at 0, it would say that we're at 1 or 2 miles an hour. So we need to add it as a proportional value. So we're going to add a small amount of extra in there in order to bring it so that it's displaying similar to what OEM gauges would be and give us that tiny little buffer just for safety's sake. So if it's running at 38 and we want it to show 40, we can just do 40 divided by 38, which shows us it's adding 5%. So what we want to do is edit this graph and then multiply those two things together. So multiply it by 0.00621731 gives us this value. So if we just copy that and paste that into here, this is going to take the original value, convert it from kilometers an hour into miles an hour, and then give us a 5% safety buffer. So if we add that graph, there we go. So this is roughly running at the 40 miles an hour that I thought I was driving at, which is great. Same with the 30. So I had a bit over here. Now I was running a little bit over 30, and that's right. So yeah, this all seems pretty accurate to what I was actually doing. So when we want to put this into our Arduino code, we can now just edit the selected graph. We need this number because that's important. We're going to change the candidate in the code that I already had. So I had a candidate for speed, which is 2D1. We're not actually using 2D1 anymore. We're using 354. So if ID 354, then process the speed and pass the bytes, all the bytes through to processing speed. I've got that in here. I want my most significant bit to be 0, my least significant bit to be the one straight after it. So I have this process endian function where I can basically increase the importance of a byte by a certain number of bits. So this will do that automatically here. So the kilometers an hour, the raw value, so instead of saying constant hour value, let's say raw value, is the most significant bit, which we pass through first, and then that shifts it 8 spaces to left to basically multiply it by 256. You could do the same thing. You could multiply that 1 byte by 256 and you end up in the same spot, or we could just use it with the least significant bit. And then to get it to the miles per hour value, we're going to take that raw value and then just multiply it by our division factor. Now in practice, I might want to change that safety buffer to a larger or a smaller value. We'll play with it. It's probably going to end up somewhere between 2 and 5%. Then we're already doing a rounding on that number because it's going to be quite a long number. And that rounding will smooth off kind of any of these particularly high and low points. So this will smooth off even more when we have the rounding on it. And then we don't need to have this legal buffer here. And that's it. That's miles an hour produced. So as you can see, by using a combination of this graph and of this data analysis here, it's quite easy to go and find all of those ranged data types. So long as you have a good large amount of data that you can sit and play with and dig into. So that's a really important thing. Just, going out and capturing a load of data. Hopefully that's showing you can actually start to dig through this information and find the range type datas relatively easily, as well as showing you what the graphing view and this detailed frame information is really used for in SavvyCan. And again, free application. If you want to use this and the data that I've produced, links to both of them are in the description, so you can have a play with them and just, dig through it a little bit yourself. There will be one final, maybe, video on this CANBus analysis for the 350Z coming later on this week, where we take all the findings that we've got, so all the flag types, the range types, the big and little endian types, and we create a DBC file for them, which is a CANBus database file, which will then, when we apply it to this view, you'll see it suddenly populate this list down the side and show actually what all of the things are. So it'll make digging into things really easy because anyone else can then apply that to their data and it'll just label everything. Very, very useful. So a video of that will be coming, like I say, sometime over the next few days. But then we've got to take all this information that we've captured so far and start applying it to the new gauges. And if we look around my office right now, there is stuff out because the next steps are happening with this. And this is all custom fiberglass, all made by me, all very nice. Plus, like I say, we've got to do an additional bit because oil, pressure, battery voltage, and some other bits of information that we want, like oil temperature, don't exist on the CANBus. So we have to sense them in other ways, whether that's adding additional sensors to the car, which is what we're going to be doing for oil temperature. But oil pressure is sent by a thing that we're going to look at, the unified meter. And we're going to look at how we can listen for things that create a voltage range. So our pressure is done between 1 and 5 volts, and how we can then convert that to a number that we can display again on a gauge like this, all using ESP-32. They can try and hide the information from us, but it doesn't mean we're not able to get it. If you do want to keep up with that and see how we put that into application over the next couple of videos, make sure you hit subscribe because we have a lot of really cool stuff coming. And if you do enjoy this video, give it a little thumbs up so that I know that you're into this stuff. I can see already by the growth of this channel, we've tripled in size in the last 2 weeks, which has been insane. I'm very thankful for it, but I guess you guys are into car hacking, so let's do a lot more of it. There's tons of stuff that's going to be really cool coming up. Anyway, whatever you do with the rest of your day, folks, have a wicked one, and I'll see you in the next video. Take it easy, peeps. Bye-bye.